Photocyclization. So this is direct reaction, we can write. So this reaction already given. Here double bond, and here hydrogen is there. Photochemically cyclation is possible. So now this can combine here, this can combine, and this can combine. Now photochemically, what is the mode of rotation? Con rotation or disrotation? Is it 4n plus 2 or 4n pi? 4n plus 2 pi system. 4n plus 2 photochemical. Con rotation. Con rotation, now here trans become trans. This is trans become trans. Then this will be undergo cyclization by using iodine in presence of oxygen. Iodine in oxygen. Otherwise you write like this. Iodine in oxygen is a oxidation reaction where you will expect a cyclation. So once if it is cyclized, you will get this. So this reaction also given in exam. That is the answer. Cyclation product. So they will give like this. That is first photochemical. Second one iodine under oxygen. This is ethyl and here it is ethyl. Photochemical iodine in presence of oxygen. So this is common reaction for benzene. Cyclation, benzene substitution with the help of benzene. A reaction exit state is pi to pi star singlet only. So that is photochemistry of benzene. Cyclation reaction is very easy. With the help of benzene, external double bond involved in cyclation followed by dehydrogenation. So that is called cyclation. See, initially this benzene is not connected. Now later on they are connected. That's why it is called cyclation. So this application is given up to here pericycle, then followed by dehydrogenation. So that is about photochemistry of benzene, olefin and carbonyl compound. So it is almost all end of photochemistry. Only Barton reaction is there and photooxidation. Only two topics are there. Now photochemistry of some miscellaneous groups. Photochemistry of miscellaneous groups. So mostly dihalides. So dihalides involve in photoelimination. If I give anywhere dihalide, go for photoelimination to give olefin. Which means if two halides are given adjacent to each other, dihalides, photochemical if they given, go for elimination. Right, olefin. Suppose if the two halogens are present on benzene even, here X and here X, photochemical anywhere if they given dihalides, then your answer is what? Benzene. So remove this group and this group, this radical put double bond. And there is a loss of X2. X2 is removed out, here also X2 is removed out. So dihalides always undergo photoelimination. Azo derivative. Nitrogen double bond. This is azo derivative. Azo. Here reaction exit state is N2 pi star singlet. Azo derivative. Nitrogen double bond is there. That is called azo. And they have a N2 pi star singlet exit state. So they will show nearly two reactions. Two reactions are possible. First one, cysteine isomerism. First one, cysteine isomerism. Here if nitrogen double bond is present, here this is trans isomer. Photochemically possible to give cis isomer. Trans isomer can be converted to cis or cis to trans, both are possible. Photochemically we can convert cis to trans, trans to cis. Even aliphatic groups also get interconverted. CS3 and here one more CS3 trans. Trans photochemically have a tendency to give cis. This is CS3 and here one more CS3. Cysteine isomers are possible with azo derivative. Second reaction, loss of N2. Here nitrogen double bond with 2 alkyl. Photochemical, if I irradiate, there is a coupling of Rn or there is a net loss of N2. So remove these two and you will get dimer. 2 alkyl parts are get joined together. Here nitrogen double bond, photochemically activated. So here there is a net loss of N2. There is a net loss of N2 takes place photochemically. So break this bond and break this bond, join these two. And here also same. Break this, join these two. N2, common loss of N2, one more is cis trans isomerism. Both are possible. So it depends upon the wavelength, irradiate wavelength. Based on the wavelength, your answer changes. So mostly 303 nanometers. So this is around 225. If they not mentioned lambda, wavelength is not mentioned, on the time both are possible. So this all are around 220, 230 like that possible. And this is around 300. All are around 300. Cis trans possible at low lambda, low energy lambda, not low wavelength of lambda, low energy lambda. This is low energy lambda, here high energy lambda. Diazomethane, photochemistry of diazomethane or photolysis of diazomethane. Diazomethane. So what is diazomethane? Diazomethane, CH2, nitrogen double bond, here minus and this is plus. It is showing a equilibrium like this, CH2 minus, nitrogen plus, we can write, or else we can write directly CH2N2. Many ways you can write diazomethane. CH2N2 is called diazomethane. So if I take any diazomethane, CH2N2, photolysis, there is a generation of carbene. Carbenes are going to be generated. Photolysis of diazomethane always generate carbene. This is carbene. Suppose carbon, nitrogen, here plus, here minus, here if methyl and here one more methyl is given. So dialkyl carbene, which means carbon carry 2 methyls and there is a net loss of N2 and there is a formation of 2 electrons on carbon, that is called carbene. Photolysis of diazomethane generates carbene. Do you know carbene involved in which reactions? So carbene involved in insertion, addition, rearrangement reactions. These are most common reaction. Insertion, addition, Siemens-Smith reaction possible, and one more is Wolff rearrangement, untested rearrangement. All are possible after generation of carbene. See, our target is not carbene. Our target is what happens when you make photolysis of which one? Diazomethane. Diazomethane and photolysis give carbene. Carbene is different reaction. After getting carbene, this carbene may undergo insertion, addition or rearrangement. Rearrangement, carbene famous reactions are untested rearrangement or Wolff rearrangement. That is carbene intermediate reactions. Diiodomethane in presence of zinc copper couple. Then what is your answer? Formation of cyclopropane. So this is called Siemens-Smith reaction. Carbene intermediate reaction. Diiodomethane in presence of zinc copper couple, that will give cyclopropane. That is Siemens-Smith reaction. Siemens-Smith reaction proceed with which intermediate? Carbene. Photolysis responsible to generate carbene. That carbene added on double bond. So that is Siemens-Smith reaction. So it is an example of addition. Siemens-Smith is an example of addition reaction. Conversion of olefin to cyclopropane. Olefin to cyclopropane is called Siemens-Smith reaction. Now here reagent is diiodomethane in zinc copper couple. See, this is photolysis in presence of silver 1 oxide. Now this negative charge migrate here, this R migrate from here to here, N2 will be removed out. So after migration of this R, CH double bond O, what is this? This is ketene. This is called diazo ketone. So this is called Wolff rearrangement. Conversion of diazoketone to ketene is Wolff rearrangement. What is intermediate? Carbene. What is intermediate here? Carbene. This is called Aunt-Eisted rearrangement. This is also carbene intermediate. It is proceeded with Wolff rearrangement. See the difference between this and this answer? R and carboxylic acid is there, but here R and carboxylic acid separated by CH2. That is called homologation of carboxylic acid. So this is called Aunt-Eisted rearrangement. Aunt-Eisted rearrangement. Total reaction. Homologation of carboxylic acid is Aunt-Eisted. diazoketone to ketene is Wolff rearrangement. Conversion of olefin to cyclopropane by using diazomethane to cyclopropane in zinc copper couple. Copper activated zinc. Okay, copper activated zinc. Copper is activating zinc. That's why it is called zinc copper couple. So what is the use of copper? Copper is activating zinc. So this molecule will give a carbenoid. That carbenoid helps to join these two. Alkyl azides. So alkyl azide we can write like this: R attaches to nitrogen with 3. So this we can also write like this: here plus, here it is minus. This is called alkyl azide. Rn3, Rn minus, nitrogen, nitrogen triple bond. Alkyl azide. You need to remember these names. Wolff rearrangement intermediate carbene. Siemens-Smith intermediate is carbene. Okay. So even untested intermediate is carbene. See, here photochemical silver 1 oxide, here also photochemical silver 1 oxide is given. This step is Wolff rearrangement. Within untested there is a Wolff rearrangement is there. Within untested Wolff rearrangement is present. Wolff rearrangement is not a separate reaction. While doing any untested, in that middle one step is there, that step is belongs to conversion of diazoketone to ketene. That is called Wolff rearrangement. Now, I am taking alkyl azide on photolysis, that is responsible to give nitrene. Nitrene is intermediate in this one. Nitrene formation. Nitrene. What is the valence of nitrene? 1. What is the valence of carbene? 2. What is the valence of nitrogen? 3. Nitrogen valency 3. Carbon 4. Here nitrene valency 1. Monovalent nitrogen electron deficient species, that is called nitrene. Carbon divalent deficient species is carbene. Carbene, carbon not same. Carbene is a electrophile. Nitrene is also a electrophile because there is a presence of 6 electrons. 1, 2, 3, 4, 5, 6. Valency of nitrene is 1. Same. They involve in insertion, addition, rearrangement reactions. So your most common rearrangements are Hoffman rearrangement, Curtius rearrangement, Lawson rearrangement and Smith rearrangement. So these are the common nitrogen rearrangements. So you will see in rearrangements, carbon rearrangements are untested, Wolf, but nitrogen rearrangements are Hoffman, Curtius, Lawson and Smith. See, in short I will give, when any primary amide is there, this is called amide. Amide reacting with sodium hydroxide in bromine. So there is a formation of a amine. There is a formation of a amine. This is called Hoffman rearrangement. Primary amide to what? Hoffman rearrangement. Conversion of primary amide to primary amine, reacting with sodium hydroxide in bromine. So what is intermediate? Nitrine. Nitrine intermediate. Okay. Next, RC double bond O. This is called acyl azide. Acyl azide on photochemical or thermal. If you irradiate, then that will give isocyanate. This is called Curtius. Curtius rearrangement. Acyl azide to isocyanate. So hydroxamic acid, hydroxamic acid to amine. This is called Lawson. Lawson rearrangement. Starting material, final answer, intermediate. They are sufficient for any rearrangement. Only thing, identification. Very fastly, without any doubt, you need to recollect the any name reaction. Hoffman, primary amide to amine. Intermediate is what? Nitrine. See, our concept is not nitrine. Our molecule is alkyl azide. When alkyl azide photochemical irradiated, what is that? Nitrine. Nitrine further undergo chemical reactions. That chemical reactions you need to know. Okay, mostly insertion, addition, rearrangement reaction. Hoffman, Curtius, Lawson and Smith. They are top reactions of nitrogen rearrangements. So Curtius is acyl azide, not alkyl azide, acyl azide. So this is on treatment with hydrozoic acid in H2SO4, carboxylic acid. It is responsible to give amine. This is called Smith. This is Smith rearrangement. Not Smith reaction. Smith reaction is also there. Smith reaction is different. Smith rearrangement is different. You need to know what is starting material involved in that reaction. Smith rearrangement and Lawson rearrangement, Hoffman rearrangement, primary amide. Definitely this nitrogen should carry two hydrogens. Then only it is possible. Suppose if this nitrogen having only one hydrogen, no reaction. And if there is no hydrogen, no reaction. Definitely it is primary amide only. Primary amides reacts with sodium hydroxide and bromine, that will give primary amine. Only primary. Primary amide to primary amine. No secondary, no tertiary. Intermediate is isocyanide. This is intermediate in this one. And that is responsible to give primary amine. In all this reaction, common intermediate is this one. But this cannot be survived when I use basic medium or water or acid medium. That's why I can't write isocyanide. This I will give in rearrangements. But you need to remember what are the top reactions involved in carbene and nitrene. So that is about azides and diazomethanes. Photochemistry of azides and diazomethane. Only thing, they will generate carbene and nitrene. They will involve in further reactions. Photochemistry of alkyl hypohalite. Clear? See, this is called alkyl hypohalite, ROX. So when alkyl hypohalite on photolysis, there is a generation of alkoxy radical and halogen radical. These points you need to remember. Alkyl hypohalite on photolysis generates alkoxy and halogen radical. Suppose see, if I take any tertiary butyl over here, tertiary butyl attaches to chlorine, photochemical if it is irradiated, then what happens? See, break this. After breaking here, this carbon carry alkoxy or not? This is alkoxy and here chlorine. Now break adjacent carbon alkyl group. So after breaking, what is your answer? This carbon radical, this radical becomes carbonyl compound or not? This is carbonyl compound. Then there is a formation of methyl chloride. This is a common answer. So photolysis of hypohalite always give alkoxy and alkyl radical. Alkoxy and alkyl radical. And these two radicals are stabilized by this cleavage. That is the answer. So this point you remember in hypohalides, when any alkyl hypohalite having a delta CH group, when delta CH carbon is present, alpha, beta, gamma, delta means fourth carbon having a carbon hydrogen, on that time photochemical sodium hydroxide definitely they will give. Without sodium hydroxide also possible, but commonly sodium hydroxide is preferred to get excellent reaction. So this particular mixture responsible to give what? Cyclic ether. Okay, so see the reaction. What is this group? See, is it alpha? This is beta or not? Beta, gamma, and what is this? Delta. Delta carry how many hydrogens? 2. Minimum 1 is required. Then photochemically, if they irradiate, then what happens? See, this carbon oxygen bond formation takes place. Remove one hydrogen from delta carbon, join delta carbon and oxygen by removing halogen. That is the answer. This is very, very important point. So mechanism C, here chlorine is given photochemically, break this bond. So after breaking this bond, there is a formation of radical. Chlorine is removed in terms of chlorine radical. Then this hydrogen is going to break here. So that hydrogen is going to remove in the form of radical. See, here one radical is there or not? I am breaking this one. This is one radical, here one radical. This radical start moving from here to here like this. So now this radical will generate a new bond between them like this. It is moving from carbon to oxygen. So whenever if this movement is observed, then what happens? Oxygen will take that and here you will get radical. So on that time, remember second molecule of same. Second molecule is going to break chlorine and this chlorine will be added here. Remember, this chlorine is not going to be added here. Second molecule chlorine is added here. This point I will ask in somewhere, be careful. So this chlorine, second molecule chlorine added here. Then what will get? Here there is a chlorine formation. And what about this? Here what will get this one? This, will you get this one? If this molecule donate chlorine, will you get this or not? Okay, now this is on treatment with sodium hydroxide. This proton migrate here, then here which charge you will get? Negative charge. Now this will attack here, chlorine will be removed out. So once you will get this answer. This is a real mechanism. So generally students what they will do, this is not CSR examination in theoretical pattern. After removing this chlorine radical, remove this hydrogen and transfer, you will get this one. This chlorine you will add here. You will get same molecule or not? If add this chlorine, but actually that is not takes place really. Okay? Own molecule chlorine will not be added on carbon. Second molecule chlorine added on first molecule carbon radical. If you know this point, Barton reaction is easy for you. Next is Barton. If you know this one, Barton is very easy. Photo Barton. 4 marks question repeating in that Barton reaction. alkyl nitrites. So RONO is called alkyl nitrate. Alkyl nitrate on photolysis, mostly 330 nanometers has been used. There is a generation of alkoxy radical, then there is a generation of nitrosyl radical. Nitrosyl, what is this? Alkoxy radical. Is it similar to alkyl halide or not? Alkyl hypohalide, and this almost all same. But in place of NO, what is written? Halogen. Alkyl nitrates, RONO on photolysis will give alkoxy radical and nitrosyl radical. If alkyl is a tertiary butyl having no delta, here O double bond O, photolysis, can I write same way what I written in alkyl hypohalite? This is CH3O radical and here it is NO radical, and this is further joins this, and your answer is what? Acetone and CH3NO. So after breaking this bond, this and this double bond, this will migrate here. Botan reaction, also called photo-botan, both are same. Botan Mecomb is different, Botan is different. It is only a Botan reaction. In some books they will give photo-botan, but photo-botan, Botan Mecomb not same. Botan reaction belongs to alkyl nitrate. See, Botan reaction belongs to this molecule. That's why first I explain that molecule property, then I am discussing corresponding name. So this is most important reaction for CSR examination. Very few reactions are there where you will expect a 4 marks question straightforwardly. In that one, Botan is one of the top reaction. Okay, Shapiro reaction, Botan reaction. Okay, Essen-Moser Tanabe fragmentation, Suzuki coupling, Heck reaction, Sono-Geshira reaction. These are the top reactions where you will expect straightforward 4 marks question. So Botan. See. Right. Alkyl nitrates having at least 2 delta CH, at least 2 delta CH. Here CH means only carbon, 2 hydrogens. Don't think 2 carbons. Carbon is 1 but hydrogens are 2. That is called at least 2 carbon hydrogens. On direct irradiation, produce gamma hydroxy oxime. gamma hydroxyoxime is known as Barton reaction. So this point you need to remember. Hydroxyoxime, alkoxy, alkyl nitrite. Starting materials are very important in Barton. Alkyl nitrite having at least 2 delta carbon hydrogens. Here delta carbon hydrogens. Here hydrogens are more than 1. If one is present, you will not get Barton reaction. Minimum 2 hydrogens are required. Maximum 3. More than 3 we can't write. So this is that reaction. Alkyl nitrites on photolysis, gamma hydroxyoximes. So one famous molecular rearrangement is there for oximes. What is oxime? Beckmann. If oxime is given, definitely Beckmann. So that's why when Barton is given, they will ask Beckmann question. One more. Next interconversion, Beckmann. Barton reaction, answer is Beckmann. Beckmann starting material. After getting oxime, next is Beckmann rearrangement. Barton and Beckmann rearrangement. So here see, I am writing a alkyl. See, this is that molecule. What is this? Alpha. What is this? Beta. Gamma. What is this? Delta. This carbon is your target site. Same molecule. Last I written. Here what I written? Halogen. In place of halogen what I written? NO. So your answer is delta. Remember, first you need to break here. Break here, add this hydrogen from here to here. If you add hydrogen, what is your answer? OH. Then this carbon, nitrogen double bond, and write down OH here. If you write OH, what is this? This is oxime. See, with respect to this, what is this? Alpha. What is this? Beta. What is this? Gamma. Gamma hydroxyoxime. Carbon, nitrogen double bond, and OH. See, oximes on hydrolysis. Oximes on hydrolysis produce carbonyl compounds. So here you will expect a carbonyl compounds here. See, whatever oximes you are getting, this oxime, now I am doing hydrolysis. Hydrolysis, mild acidic combinations I am using. So here this is responsible to give a corresponding carbonyl compound. This interconversion also possible. Oxime upon hydrolysis, this remove this double bond, put oxygen. So now what is your answer? Alpha, beta, gamma. Gamma hydroxy ketone. See, always delta carbon hydrogens and nitrate groups are cis to each other. Cis or syn to each other. They should be syn to each other. Then only this reaction possible. If they are trans, no reaction. Always delta carbon hydrogen, nitrite. These groups are, this group and this both are separated by 0 degree. Then only this reaction possible. So photochemical, break this. So after breaking this, here will get a radical. And what is removed? NO plus. Nitrosyl is going to be removed. Here how many hydrogens are there? 2. Is it delta? Alpha, beta, gamma, delta. Remove one hydrogen. This hydrogen is transferred from delta position to alkoxy radical. Here one radical is there. So it will be stabilizes this two. It is also stabilizes this. It is a transition state. So after that, there is a formation of hydroxy and here radical. Right? Then this nitrosyl never transferred here. Second molecule of this one, nitrosyl will transfer over there. See, here I am writing R, here I am writing NO. Already radical is there. Break this. This nitrosyl comes over here. Now what will you expect? OH. What we are getting now? N double bond O or not? So what is the byproduct of this one? Byproduct of this one is this. So this is R. You will get O radical, right? This one comes here. See, this nitrosyl, first molecule nitrosyl radical never added to same molecule delta carbon. This nitrosyl comes from second molecule. Second molecule alkoxy radical. See, this one take this hydrogen. One more time. This will take here. Then you will get this one. This one to this or not? If this hydrogen transfer from here to here, you will get this one. This will take nitrosyl radical from third molecule. Then fourth molecule, fifth molecule like that. Right? Like that reaction is going to be proceed. This reaction not exist when you take only one molecule. When you take only one molecule, don't think that this nitrosyl comes from here to here. That is dead slow process. That's why when one molecule is taken, yield is very poor. If second molecule is not available, then this will come over here with a delay process. If you take more amount of nitrosyl, alkoxy, nitrates, if I take n amount of nitroxy, alkyl nitrite, then this reaction is excellent. If you take only one molecule, reaction is not easy. So, after getting this C, here hydrogen is there or not? This hydrogen migrate from here to here. And this double bond migrate here. What is this? Tautomerism. So, if it is undergoes tautomerism, here it is OH, carbon, nitrogen, double bond. And what about this? Hydroxy. So, alpha, beta, gamma. Gamma hydroxy oxime. Up to here it is a Barton. Up to here it is Barton, remember. Up to gamma hydroxyoxime is Barton. Preparing ketone is not Barton. It is applications of Barton. From Barton product to this, it is an application. But up to here it is a Barton. This is further hydrolysis with mild acidic medium. So this is responsible to give keto. So this is alpha, beta, gamma. Gamma keto, gamma hydroxyketone. But this is not, from here to here it is not Barton. Up to here it is Barton. This is called Barton product. Which among the following is the Barton product, they will ask. What is Barton product? Hydroxyoxime. What is Barton starting material? Barton reactant. Alkyl nitrite. Suddenly it is not easy to remember. Oxime. See, oxime only two reactions. Only two reactions are there related to oxime. One is Beckmann, other is Barton. Over. See this reaction. Here I am writing alcohol. When alcohol upon treatment with NOCl. What is NOCl? Nitrosyl chloride. Okay, so on that time this oxygen lone pair will directly attack on nitrogen, chlorine will be removed. So initially what I used? Alcohol. Okay, is it alcohol or not? So this alcohol, what is this carbon? Alpha, beta, gamma, delta. Right? So this is a nitrite. Alcohols reacting with nitrosyl chloride. This is called nitrosyl chloride. You will get alpha, beta, gamma, delta. Alkyl nitrite. This alkyl nitrite on photochemical irradiation. Then what is your answer? Your answer is Barton product. What is Barton product? You will get double bond N and this is OH. See, initially what I taken? Alcohol. Now alcohol one more time reappears. Okay. So after getting this alcohol, then see, this is upon acid hydrolysis. Then simply break this. After breaking, your answer is, here this is alcohol and this is this. So what about this? Alpha, beta, gamma, delta. Initially what I taken? Alcohol. So this position is my target position. Here I want to do some reaction. So this particular carbon I want to create a carbonyl compound. This carbon I want to create carbonyl compound. First alcohol converts to alkyl nitrite. Then go for Barton reaction. Then acid hydrolysis. Then final answer is what? Alpha hydroxyketone. With respect to this, which is the dominating functional group? Ketone. So this is alpha, beta, gamma. Right or not? Same molecule repeating on final step or not? But only thing is, this alcohol initially I used And this position I created a new functional group. That can be done by using intermediate Barton reaction. From here to here Barton. From later on we are preparing the keto functional group. So it is an indirect method to prepare a keto group at delta position for alcohol. In this alcohol, if I want to prepare a keto group here, which is an indirect method, Barton is an indirect method. So from here to here Barton, from there onwards a simple interconversion from oxime to ketone. This interconversion they asked in exam. So take up to here applications of Barton reaction and previous year's Barton reaction questions we will discuss in your next class. Okay. Just revise this concept and come. It is most important one for your CSR examination. This one and Beckman interconversion. Okay, only one more class is sufficient to close photochemistry. Only photo applications of Barton, one more is photo oxidation is there. For 2pi 2pi cycloaddition, 4pi 2pi cycloaddition. Okay, so photo in reaction, that all are very simple, but only one class is sufficient to close photochemistry chapter. But try to stress Barton reaction. What are the key points are given right now? Just revise that points and come in your next class so that it will be very easy for you. Applications. So what is the requirement? Delta carbon hydrogen. Delta carbon hydrogen is present for any alkyl nitrate. That will give, what is your answer? Alpha, beta, gamma. Gamma hydroxy oximes. Delta to gamma. Delta to gamma hydroxy oxime. Then finally gamma hydroxy ketone. Okay. We'll stop here. We'll continue in your next class. So evening schedule, today evening schedule will be given in your WhatsApp. And tomorrow there is no class. So tomorrow we are declaring holiday. Next class is on Monday. Morning session class I am saying. Tomorrow morning there is no class. If any change in timetable is observed, that we are going to update in your WhatsApp group. But till today there is no morning class. Evening schedule will be given in your WhatsApp group. Okay, we'll stop here.